Hi everybody! In this video we're going to start chapter 10, and let me just tell you a little bit about chapter 10 first and then we'll go into 10.1. So chapter 10 is going to be on infinite sequences and series. And so what that is going to look like, and I'll give you some examples down here so you understand that, are either lists or sums of terms. And so why do we want to work with these? Why does this matter? Well, here's an application. An application for sequence and series is that they can be used when making computations with complicated functions. And so some functions that are difficult to compute can actually be replaced by infinite series. And so that's one of the reasons why we're going to be studying these sequences and series, because you can use them to replace a more complicated function that's harder to work with and compute with. You can compute with the easier version, the infinite series. And so the vocabulary that we want to know getting into this chapter is that when we say sequence, we mean an infinite list. Okay? And when we say series, we mean an infinite sum. So basically the difference is, are there plus or minus signs in between the terms? If so, that would be considered a sum, therefore it's a series. If it's just a list of terms with like commas in between, that would be considered a sequence. Okay, so let's get started with 10.1. Alright, jumping right into 10.1, sequences. So our definition for sequence, a sequence, as we said before, is a list. It's a list of numbers in a given order. So the order does matter. Okay, so if it's the same numbers in the list but the order changes, it's a different sequence. Here's an example for us. 2, 4, 6, 8, 10, and then so on, and then 2 times n, so on. So this is an example of an infinite sequence. Notice it is a list and it is infinite. Okay, so infinite sequence. So let me give you some information about the notation you're going to see. The first term, 2 in this case, is described as a sub 1, excuse me. And so the subscript tells you which term number. So this is saying this is the first term in the list. If I pick another term, let's go with 10. If you count where you're at in the list, 1, 2, 3, 4, 5, this is a sub 5. So 10 is the fifth term in the list. And you can say a sub 5 equals 10. And then 2n, well, this one over here, we would call this the nth term. So the subscript would be n. So this is a sub n, and this is the nth term in our sequence. And so this is a general term. This could be anywhere on the list. It could 2 and 4 and 6, all these numbers I've already listed are technically nth terms, but they have specific numbers because I know where they're at on the list. Okay. Now, the nth term, because it represents any number on the list, there's actually a formula or rule that can be used to describe each of the terms in reference to the nth term. So in general, so a term or rule can describe each term. So n, let me just make a mention about what n is called. So this is an example of a sequence where the letter n is the index. So n is the index, and it tells us about, in general, our nth term on our list, or the rule for how to find these numbers on our list. And so let me just show you an example for how 2n would work. Let's use a number that's already on our list. I'll switch colors here. Let's say we wanted the third term on the list. Okay, let's pretend this was blank for a second. You already know what it is. You could tell just by guessing, even if I hadn't put the 6 there to begin with. 2, 4, blank 8, you would have probably known it was 6. But if you knew that this rule was 2n, well, if this is in the third spot, we know that this term is a sub 3. The rule is 2n, so n in this case is 3, so 2 times 3, so that term has to be 6. Okay, so that's how that works. Let's go ahead and look at a more in-depth example of the type of sequences that you're going to see. Taking a look at our first couple of examples. So starting here, our first example, first of all, These squiggly braces just mean the set. So the set containing what's inside. So this is saying that this is the set of all a sub n terms, and then the rule for it is 1 over n is going to be how you find each term. Again, the squiggly braces just means that it's a set containing those terms. This notation on the side, if you kind of think back to integration, this is similar notation. This is the index. It's telling you from n is 1, you start when n is 1, and you go all the way until n is infinity, and that's how you create this set or this sequence. And so in this case, I'm going to use the set brackets just to say I'm containing these values in one set, and I'm going to start with my rule. So each term in my list, for the first term, a sub 1, I put a 1 where there's an n, and it also tells me I'm starting at 1 for n. So 1 over 1, which is 1. Then my next term, a sub 2, I would say 1 over 2. And then my next term, a sub 3, would be 1 over 3. And I just keep doing this. That's the rule for this sequence. It would be 1 over 4, and so on. And then in general, 1 over n, but it keeps going until infinity. Okay. So for this one, let's see what that will look like more visually. I have my coordinate axes over here. My input is n. I plug in n, and I get out a term value or an a sub n value. Okay. So I'm going to just label my coordinate axes based on the numbers I'm dealing with. It looks like 1 is like my biggest number on my list, and the number 1/2 is smaller, and then 1/3 is smaller. So when I label this, I'm going to start with 1 right here, and I don't need to put a whole lot of other numbers because of what's in my list. Now what I'm plugging in is n. N started at 1, then I plugged in 2, then I plug in 3, and so on, and so on, and so on. And so let's just plot these few points and see what this looks like. When I plugged in 1, I got out 1 for this sequence. When I plugged in 2, I got out 1/2, which would be about like right there. 1/3 is a little less. When I plugged in 3, 1/4 is smaller than that, 1/5 is smaller than that, and so on and so on and so on. Okay. We'll talk more about this in just a second, what's happening with that graph. Over here, another example. So this one's not given with a rule, but we're going to work the other direction and we're going to find the rule. Back here, you were given the rule, you found the terms in the sequence. This time we're given the terms in the sequence. Well, what's the rule? And so we know, in general, a sub n is our nth term. It's any term on this list. It's this one when a is 1, this one when a is 2, and so on. Okay, now, if you've never seen something like this before, it might take a minute to figure it out, but I'm going to show you how you identify a sequence like this when the terms switch signs. Positive, negative, positive, negative. So what's happening, if you think about it, is you actually have a -1, if you think about it like this, that's changing powers. Anytime you square something, if it was negative, it turns positive. If you raise a negative to the 3rd power, it's negative also. If you raise something to the 4th power that's negative, it turns back positive. And then the 5th power, it would be negative again, and so on and so on and so on. And so what's going to happen here is, I'm going to say n plus 1 for the exponent. And watch why I do that. If I picked n for the exponent, let me just show you what would happen. If I start with n as 1, we usually start with n equaling 1 because that's the first term. This is a sub 1, so n is 1. Sometimes it'll be told to you different, but not very often. They'll say something like n starts at 0 or something like that. So in this case, if I plug in a 1, let me pretend that I didn't put the plus 1. If I plug in a 1, -1 to the 1st power is still -1, and that's not our first term. So that's why that rule, if I would have just put n, that wouldn't have worked. So if I say that this rule has an n plus 1 for my exponent, look what happens. If I plug in a 1, -1 to the 1 plus 1 power is -1 squared with parentheses, which is positive 1. Let's check the next term. Let's check a sub 2. If I plug in a 2, okay, that was for a sub 1. If I plug in a 2, -1 to the 2 plus 1 power is -1 cubed in parentheses, which is still -1, which is my next term. And so this is the rule for this sequence. And whenever you see a sequence where the terms switch signs like this, there will be -1 to a power somewhere in that rule for it. So let's go ahead and graph what's happening here. Notice the highest number in your sequence is 1, the lowest is -1, so you don't have to go very high and low on your a sub n axis. 1 and -1 here. And then we'll just start with n is 1, 2, and so on like we did before. This is the n axis. And then if I start plotting the terms in our sequence, when we plugged in 1, the first term was +1. When we plugged in 2, we got -1, plugged in 3, back to 1, plugged in 4, you'd be back down at -1, and so on and so on and so on. Okay, so going back to this graph and this graph for our points, what we're interested in when we're thinking about sequences is what happens to them when we keep going. How do they behave when n gets large? And so on the first one, how does this one behave? What's the behavior? What happens to this sequence? So as n keeps going, or n approaches infinity, well, this sequence, 1 over n, where does it go? Does it approach something? How does it behave? Well, if you look at the graph, look what's happening to it. We started here at 1, it's going down and down and down. It's getting smaller. This is 0. It's getting closer and closer to 0. And then just think about it for a moment. Is it ever going to go underneath this axis here, this n axis? Is it ever going to be negative? If I plug in 1,000,000, 1 over 1,000,000, it's so tiny of a number, but it's still positive. So this is going to keep going lower and lower towards 0, and it's going to get super close to 0. So as n goes to infinity, our sequence is actually approaching 0. So if you're not familiar with the arrows, you might be from limits, but this just means approaches. So you can say 1 over n approaches 0. That's the behavior. How about this next one? Well, when we were plugging in our term, our index values, 1, 2, and 3, and so on, well, what was happening to our sequence values? Okay, so same idea. As we keep going, as n goes to infinity, over here, this expression for our nth term, let me just rewrite it, -1 to the n plus 1. What's it doing? Well, n goes to infinity to the right. It's 1, -1, 1, -1, 1, -1. It's just going to keep bouncing back and forth. So as this n keeps growing, this sequence, it just bounces or oscillates. Bounces back and forth, or oscillates between 1 and -1. Back and forth from 1, or between, that might be a better word, between 1 and -1. Okay, and so we're going to define this a little bit more clearly, but these two behaviors are things that we're really interested in, and when we have the behavior of a sequence when it actually approaches something, we say that it converges. Okay, so it converges to what it approaches. Okay, it's converging on 0. When it doesn't seem to converge to one value, when it doesn't seem to go to just one number, in this case it's bouncing back and forth, as in this example, we say that this one diverges. Okay, so let's get into those two definitions a little bit more formally. So convergence and divergence, the sequence a sub n converges to a certain number. We're going to call that number L. So it converges or approaches this number L if the following is true. So notice I have absolute value bars. Before I even put what's supposed to go in there, that represents a distance. And so what the distance is going to be is the distance from a sub n to this approached value L. So if the absolute value from a sub n to L, or the distance between our term number and this L number, if that distance is small enough, that's what this is saying. So it's less than some number epsilon, where epsilon is just an arbitrarily small number. So if this distance is small enough between our term number and our L number, then we say it converges, and this is true whenever our index little n is greater than some other capital N value. So it's a little bit mathy here, and there is more to this definition than I'm telling you, but I'm just going to kind of briefly break down what this is saying with our example we already looked at. So consider the example where our sequence was 1 over n. I regraphed it. I just sort of made more details on the graph this time and put some more coordinates on our a sub n axis. Now, we already looked at this and we thought, okay, this looks like it's approaching 0. Like this sequence, the terms are going to 0 as we keep increasing our n value. So we think in this case that L is 0. This is the number that our sequence converges to. So let's prove that it in fact does do that. So according to this definition, our sequence converges to this number if this inequality here is true. So let's fill it in. So we have a sub n, in our case it's 1 over n, minus L, in our case that's 0, should be less than some number we're calling epsilon. Okay? Let's solve this inequality for little n. So absolute value, we can go ahead and take this off because it's just 1 over n in here, and n is starting at 1, so it's always positive. So you can kind of just drop those absolute value bars, and this is 1 over n is less than epsilon. Okay, a little bit of algebra, multiply both sides by n, divide by epsilon, and you're going to get that 1 over epsilon is less than n. Well, if you look back at our definition, little n should be bigger than some number, capital N. And capital N is some integer number that we have to just figure out from this process, which we are figuring out. And as long as little n is bigger than this number, notice what this is saying. Let me flip it over so it's a little bit more clear, and I'll write it right up here. So if I just rearrange this, this says little n is greater than 1 over epsilon. We'll look at this definition. Little n has to be greater than big N. So in our case, we're just going to say that capital N must be 1 over epsilon. So I am doing like a semi-mathematical proof with you. You won't really have to do this in too much detail, but I just want to show you why this is true, what this definition is saying. So then let's plug this into what we're talking about for our definition. And let's pick a specific epsilon value. Okay, I'm going to just make something up. I'm going to say, okay, how about we're going to let epsilon equal 0.2. Okay, so look at our graph here. So if epsilon is 0.2, this is remember what this was saying, the distance from our sequence number to this L number that we're approaching, it has to be less than this amount, epsilon. So in our case, less than 0.2. So I'm going to draw a line going across our sequence that's 0.2 away. Notice this is 0.2 away from our L number. L was 0, so this is an epsilon value of 0.2 away from 0. Okay, so what is this really saying? So now we have that n, okay, is 1 over epsilon. We decided let's just pick 0.2 for our epsilon value. We could have picked anything, but I picked something pretty small, 0.2. And so if I plug that in here, we know that this is 1 over 0.2. And so if you solve for capital N equals 1 over 0.2, solve for capital N, you're going to get capital N is 5. So from our definition, I'm just going to erase and fill in our definition. As long as little n is more than 5, okay, little n is more than 5, then our distance from our term value to our approach value should be less than 0.2. And let's see if it makes sense. So if I go to my term number where n is 5, am I less than 0.2 away from 0? So n is 1, 2, 3, 4, 5. There it is. And anything past this, so anything where n is bigger than 5, notice that you are less than 0.2 away from 0. All of these term values would be closer to 0 than 0.2, a distance of 0.2. So yes, this worked. By this definition, I know it was kind of mathy there. Our function or our sequence does in fact converge to 0. And so if your sequence converges, over here our note, if a sub n converges, then hopefully this is maybe what you might have been thinking about already, then the limit as n approaches infinity of your sequence, a sub n, is that number L. So I avoided saying it, but now I'll say it. This number L was just the limit. Okay? So this number we're approaching that we're converging to is actually the limit of our sequence. Okay, if it does in fact converge. And then the last thing to note here, before we move on to some examples, is if a sub n does not converge, then we just say, then it diverges. Okay. So basically what you look at, diverges. You always are trying to figure out, well, does it converge? And if you conclude it does not converge, then you just say, well, then it must diverge. Okay, so this is a brief introduction to sequences. And then in the next video, I'm going to give you some rules and theorems, and we'll look at some examples.